All right, I think we're recording. Let's try it one more time. Here we go. All right, this is progress check FRQ number 2. It says the mass of the block is m, and the spring constant of the spring is k. Starting with conservation of energy, derive an expression for the speed of the block as it passes through the position x is equal to a over 2. So we want an expression for the speed of the block, right? That's going to be v as it passes through position a over 2. Express your answer in terms of m, k, a, and physical constants. That would be like g or something like that. All right, let's take a look at the situation. What's going on at a over 2? So I've drawn the location a over 2, right? At this position, the block would be moving. We don't know if it's moving left or moving right. It could be either one. But the bottom line is it has velocity, so it has kinetic energy at that point. So at this position, right, at a over 2, it has kinetic energy. Now the spring is also stretched, right? It's not at the position x equals 0, so the spring is stretched, so it also has spring energy. So we have both of those. Now, you have to pick another position if you're using the conservation of energy equation. So the position I chose was x equals a. And the reason why I chose that position, because that's where the block temporarily stops or has no velocity, right? It's changing from moving right to moving left. And that means the velocity is 0, therefore the kinetic energy is 0. And that's just going to help us clean up our equation and solve it mathematically, right? So, but there is a lot of spring energy at position x equals a. So all of this energy here is equal to the spring energy at a. So let's take a look at what the derivation would look like. So basically, we're starting with this equation right here. Right, we're saying, hey, initial energy plus work is equal to final energy, but we know the work is 0 because there is not an external force doing work on the block. It's frictionless, sliding back and forth. So initial energy is going to be equal to final energy. It's just saying energy is conserved. So we can replace E with our two types of energy. We don't have gravitational potential, just spring energy and kinetic energy, right? So initial spring plus initial kinetic is equal to final spring plus final kinetic. Well, your initial position is a over 2, and your final position is a. Okay? So again, we're just choosing two positions, but we had to make sure one of them is a over 2. All right, so I rewrote the equation, right? Replaced u with 1/2 kx squared and replaced k with 1/2 mv squared. And I want to point out that over here, basically, we can eliminate the kinetic energy at A because that is where the block reaches the farthest point on the right, and that's where the velocity is 0. So we went from 4 terms down to 3 terms. So let's do a little bit of substitution. So right here, A over 2 is replacing x because that's the initial position. And here, and I've written velocity at a over 2. That doesn't mean divide that value by 2, just a over 2 is like a little subscript saying, hey, this is the velocity at a over 2. On the right side of the equation, the position x has been replaced with the value a. It's at the furthest distance to the right. All right, now I have multiplied each side of the equation by 2. Because I noticed that there's a 1/2 coefficient in front of all 3 of my terms, and 2 times 1/2 is 1, so we just eliminated the 1/2s. And it simplifies to ka squared over 4 plus mv squared equals ka squared. So if you rewrite it as 1/4 ka squared, that's the same thing as ka squared divided by 4, right? Then we can put the coefficient 1 in front of ka squared, right? Because multiplying by 1 doesn't really change anything, but helps us see what we're essentially doing is subtracting these coefficients. So we're trying to solve for v, so we need to eliminate this term, so we subtract it. And then when we do that from the right side as well, we have 1 ka squared minus 1/4 ka squared, which just leaves us with 3/4 ka squared. All right, the next step I did was divide each side by m, right? Because m divided by m is 1. And what I'm showing over here on the right side is, how do I do a fraction within a fraction? Well, the short answer is just move the 4 to the denominator. The longer answer is multiply by 4/4, which is 1, right? And then the numerator, you have 4 divided by 4, so those cancel. And then you do have 4 in the denominator. So we should see that 4 in the denominator. And there it is, right there. And now we have to take the square root, right, on each side of the equation. And on the right side, we'll be able to pull out from the square root of a squared and from the square root of 1/4, right? So when we do that, right, a is pulled out of the square root symbol, and the 4, you can take the square root of 4, which is 2, but you got to leave it in the denominator, and then you're left with 3k over m inside the square root sign. So the velocity of the block at position a over 2 is equal to a over 2 times the square root of 3k over m.